Okay, I think we'll go ahead and get started in the interest of time. So, welcome everyone. I think we have quite a few registrations from both India, Europe, as well as the US. So, hopefully, we'll keep increasing, growing in number as the talk progresses. So, thank you very much, Professor Rajaram, for accepting our invitation to speak at the webinar series. So I will request Professor Abhijit Chaudhary to introduce Professor Harihar Rajaram. Yeah.
Thank you, Chandra. It will be my pleasure. So, hello, everybody. I think it is fine to start saying very good morning, even though we are in different time zones. Because you can say morning if only first meet in the day. And it is my pleasure to introduce Professor Harihar Rajaram, who is a world-renowned hydrogeologist, and he's completed his undergraduate from IIT Madras in 1985. And then he did his PhD from MIT in 1991. And after spending a couple of years in Princeton University, he joined University of Colorado Boulder, and he was a professor there from 1993 to 2018. And present, he is a professor and deputy chair in the Department of Environmental Health Engineering at Johns Hopkins University. He is also a professor and president teaching scholar emeritus at the University of Colorado Boulder. Professor Rajaram was an editor of Water Resources Research from 2013 to 2018. And at present, he is the editor-in-chief of the journal Geophysical Research Letter since 2019. His research involves the applications of mathematical models, analytical, computational, and stochastic to understand the behavior of complex environmental and earth systems and to predict future trends within those systems. His recent investigations have explored the environmental impacts of hydraulic fracturing, induced seismicity resulting from the injection of fracking fluid into deep geologic formations, reactive transport and weathering in critical zones, biogeochemical impacts of climate warming in alpine and other environments, and the response of glaciers and ice sheets to climate warming. He has published around 100 journal papers in the top journals like Water Resources Research, Journal of Geophysical Research, Geophysical Research Letter, Physical Review, Transport in Porous Media, etc. And some of the papers are the seminal papers and been cited, very well cited, and probably given new directions in the area of hydrogeology and fluid mechanics. So with this, I'll stop and I'll request Professor Rajaram to deliver his speech. Research.
Thank you so much for the introduction, Abhijit. Thank you all for letting me join you remotely this morning or this evening, wherever we are. I'm trying to remember what it's like in July in IIT Madras in the July evening, just before the semester starts when things are still quiet, and you have a lazy evening in and around the stadium and Gajendra Circle. Those memories are coming back to me. Let me get started here by sharing my screen. Let me go to presentation view. Just 1 minute.
Okay.
Okay, hope you're all able to see my screen. And
yeah, you can see.
Okay, great. So as Abhijit pointed out, my recent research falls in 3 broad categories. One is subsurface energy and environmental problems that have to do with impacts of hydraulic fracturing, induced seismicity, and geothermal energy systems, and so on. Critical zone science, the form and function of the critical zone in the Earth, both in terms of weathering and soil formation on the one hand, and biogeochemical changes induced by climate change in alpine and mountain regions on the other hand, and permafrost as well. And finally, ice sheets and glaciers, applying the fluid mechanical models of ice flow to understand the behavior of Greenland, Antarctica, and mountain glaciers. Fundamentally, what connects all of them is mathematical modeling that is computational, stochastic, and analytical. In today's talk, after discussing with Abhijit, I picked a topic that is more focused on analytical solutions. It's sort of a slightly old-fashioned topic, maybe, but I'm also kind of old. So I think it's okay, it's appropriate. I have always enjoyed doing analytical solutions, and sometimes, they provide a lot of useful insights on first-order behavior of complex systems, and also they serve a valuable role in benchmarking, complex coupled process simulators, which we are using a lot these days, but sometimes, we don't fully understand the limitations of the results we're getting unless we properly benchmark them against analytical solutions in, simplified cases where we can actually find these analytical solutions. So in today's talk, the focus will be on transport with bimolecular reactions in fractured rock, reactive transport in fractured rock, essentially. The applications include alteration of the rock matrix in fractured rock systems, like in geothermal energy or other subsurface energy systems, weathering of minerals from the rock matrix in the critical zone, and also remediation of contamination in fractured rock, where often large volumes and large amounts of contaminant mass reside in the rock matrix. And if you have to clean up a site, it's a huge challenge to get the contaminant out of the rock matrix, which is largely stagnant, not really flowing water, it's immobile water. So it takes some effort to get that out of there. I'll start with the focus more on the weathering and reactive alteration problems, basically involving depletion of a mineral or some chemical that is in the porous medium, the rock matrix, by a weathering agent that is supplied in the water that is infiltrating through the fractures. In other words, the water in the rock matrix is stagnant, the water in the fractures is flowing, and it contains some agent that is reacting with some other substance that is either a solid phase that's in the rock matrix or some other contaminant that is dissolved in the pore water in the rock matrix. And although this idea of a bimolecular reaction appears simple at first glance, you can take more complex chemical systems or geochemical systems and go through mass balance arguments and transformations to put them in the form where everything then comes down to the behavior of a bimolecular system, where some reagent A is reacting with the solid phase mineral or some other contaminant P or B to produce some product. And the analyzing the behavior of this simple bimolecular reaction usually gives insights on a large range of complex geochemical systems also. So with that to motivate, what I'm going to present, which is really more focused on fractured rock, let's just start by considering the behavior in a simple idealized 1D advective system. I have some mineral at some molar concentration P naught initially in a porous medium, and I start flushing water through it at some Darcy flux Q, and the water that is infiltrating contains a weathering agent, something that's going to react with the P at some constant concentration A naught. By dissolving the mineral, there's no initial dissolved mineral concentration in the inflow, so it's kind of fresh solution. But the reaction of A with P produces C. Of course, there's a stoichiometric relationship between C and A. We don't really need to include C in this formulation of the mathematics around the reactive transport model. It's largely sufficient to consider the behavior of A and P alone. And typically in systems like this, what you find is that because of what we call solid density asymptotics, a concept introduced by Peter Ottoleva back in the mid-80s, where the molar concentration of a mineral in the solid phase is often 3 or 4 orders of magnitude larger than the maximum dissolved mineral concentrations, you can actually model the system as a sequence of steady states. The flow and transport transients are not as important. You can model the behavior of the system with the steady state advection reaction equation. And typically the kinetics in the advection reaction equation are set up in such a way that you have a reaction rate that goes to zero when you approach equilibrium or when the weathering agent is depleted, and also goes to zero when the mineral is depleted. So you need both the mineral and the weathering agent to have a non-zero reaction rate. So wherever both of them go to zero, the reaction rate goes to zero. And the overall behavior of the system is then obtained by combining the steady state transport equation together with the mineral depletion equation that keeps track of the mineral mass balance and can tell you when the mineral is being depleted. So the behavior of a system like this would be, I'm sorry, my screen seems to have gotten stuck. Yeah, there we go. Okay. So typically what happens is that showing profiles with depth of the weathering agent, dissolved minerals, solid phase mineral, and the weathering rate, as the A is consumed when entering the column, it initially sets up a profile that looks like this, basically depleting with time as it's getting consumed by the A and P reaction. Correspondingly, the dissolved mineral concentration builds up. The solid phase mineral concentration is getting depleted. It will start producing a curve like this where it was initially P naught everywhere. And then as the reaction starts to occur, you start depleting near the entrance. And the weathering rate will then correspondingly, because it depends on the molar concentrations of both P and of A, starts to have this peaked shape like this. A time will come when you fully deplete the mineral near the entrance. And at that point, then the reaction rate would go to zero near the entrance. It will also go to zero at the other end where A gets fully consumed, so that you get an intermediate region where you have a reaction, and the peak reaction occurs somewhere in the middle of a region that we can call as a weathering front, where there is both enough mineral and enough A, the weathering agent, to produce a reaction. So you form a weathering front, and as you deplete the mineral at the entrance, that weathering front starts to propagate into the system. And the shape of the profile is determined by the reaction kinetics, by dispersion, and so on. But in general, the weathering front speed is actually independent of the reaction rate or kinetics. It's largely determined by a mass balance argument, as we'll see in just a minute. Because you can see that the shape here is remaining constant as this weathering front is propagating through. If I integrate the weathering reaction rate over distance, at any time, the system integrated reaction rate is going to remain constant. We call this chemostatic behavior. Essentially, all it means is that all the weathering agent that you supply through the inflow is getting consumed before you reach the outflow. Under those conditions, you have a constant system integrated reaction rate or weathering rate. So that would be the behavior in a 1D advective system. And you can do a simple mass balance argument, asking what does it take to move the weathering front by some distance dz. You need to react out P0 times dz moles of the mineral, and you need to also fill a certain amount of pore space with A naught. And if you make this mass balance argument, you can easily derive that the speed of propagation of the weathering front is much smaller than the speed of the water itself, often by 3 or 4 orders of magnitude smaller. Okay? In effect, the weathering fronts propagate slowly, and that's what we know from observations of weathering profiles and so on and so forth. So that was a simple 1D, uniform advective system. The key takeaway is that the weathering rate remains more or less constant, pretty much until you deplete the mineral throughout the entire profile, and infiltrating solutions don't have anything to react with. They leave the domain without having reacted. At that point, the reaction rate would decrease with time. So then the question is, okay, what happens in terms of the behavior in heterogeneous media where you can have complex preferential flow? In particular, we are interested in the contrast between the behavior in fractured rock systems versus more conventional random permeability field type systems. The major difference is that in the fracture network case, which represents fractured rock, you get highly preferential advection through connected fractures. The water in the matrix blocks is largely stagnant, and if you're accessing the mineral in the matrix to react with it, you largely access it by diffusion. On the other hand, in the random permeability fields, you still have some amount of advection everywhere, even if it's smaller than the advection in the main preferential flow paths. And so overall, that turns out to be the major difference between these two types of systems. So let me just play an animation here to show the behavior of the reaction system in each of these cases. I think there's a trick to getting the animation to work when I'm in pointer mode. I may need to need to escape, and then I'm going to run these simulations here, which is basically showing that you're supplying reagent, the weathering reagent A, at the top boundary in both of these cases, and we're looking at the depletion of the mineral. The mineral volume fraction is high when it's red and blue when it's 0. So whenever things are turning blue, it means that the mineral is being depleted. So you can see what's happening, in the random permeability field case. There's a clear sense. I mean, although the advection is non-uniform, just the fact that it is advective, things tend to change a lot faster. You're able to deplete the mineral out with time. Actually, we're talking about geological time here. The animation time is, of course, just a few seconds, thankfully. Otherwise, we'll all be here into the next age of the Earth, I guess. So you can see the major differences here. In the case of the fractured rock case, you're essentially sort of eating the, consuming the mineral from around the periphery of the matrix blocks and diffusing your way inward. Whereas in a typical random heterogeneous velocity field, you get a more widespread depletion by consuming the mineral pretty much everywhere by advective flow paths that can deliver the weathering agent more efficiently. So the key difference can be summarized as follows: that you get what we call as a shrinking core behavior in the fractured rock case, where the weathering rate is high at some distance into the matrix blocks, where you have enough mineral and enough weathering agent to sustain your reaction. So in other words, things are not moving as a front through the system from top to bottom, but really the front is moving inward into the matrix blocks to start weathering them away. And correspondingly, even at late time, significant mineral volume fraction remains. And you get these large boulders that are left behind, which is quite common in weathering profiles. They're called core stones, especially in the Deccan Traps region in India. You can see a lot of weathering profiles that show these types of core stone features. Here's a nice picture which illustrates that. So we can produce this kind of behavior from running these types of numerical models to describe the propagation of weathering fronts in fractured bedrock, which is usually just below the soil system. And if we look at the domain averaged or the system averaged reaction rate in these systems, what you find in the homogeneous case, which was the 1D system that I showed earlier, you have a fairly long time when the reaction rate is constant, and then it falls off rapidly as the weathering front leaves the domain. In other words, the weathering front has started from the entrance of the system, reached near the outlet of the system. It's when it reached the outlet of the system that you start seeing this depletion. When you have the random velocity fields and still advection dominated system, all that you do to this shape is that you get a more gradual sweeping out of a more diffused weathering front from the domain. But otherwise, this depletion rate, the decrease in the weathering rate is largely caused by depletion of the mineral. In fact, in the beginning, there's a fairly long period of time for which the reaction rate is more or less constant in the system integrated manner, much as in the homogeneous case, which is really the chemostatic effect, that all the weathering agent is consumed within the domain, and the weathering rate is regulated by the supply of the weathering agent, and that was constant in all these simulations. And this, the apparent time dependence of the system integrated weathering rate, which is one of the questions that geochemists are interested in. It's not really a true time dependence, but just an artifact of the fact that the weathering front is leaving the domain, and there's no more mineral to weather because it's all been depleted. Now, in contrast, in the fractured rock system, you get a more systematic time dependence. There's an initial phase where you're starting off roughly the same system integrated reaction rate. Very quickly, you start falling off from that and going into a fairly slow decay that is brought about by diffusion limitations coupled with the shrinking core mechanism. The shrinking core mechanism basically is that, once you start depleting the mineral near the edges of the matrix blocks, the diffusion length that you have to pass through to get to the weatherable mineral is increasing. And when you have to access that by diffusion, that means that you're going to take more time to reach it. And because of that, you get a sustained decrease with time. And the question is that this time dependence is consistent with a lot of field interpretations of weathering rates in shallow subsurface systems. And the notion that you have matrix diffusion from the fractures into the matrix blocks provides a reasonable explanation for that phenomenon. One thing that's clear from looking even at these complex simulations is that the behavior in the complex fractured rock mass is largely controlled by the contrast between advection in the fractures and diffusion in the rock matrix, and of course communication between the two with fracture matrix interaction. It's fine to do numerical simulations, and what inspired this work that I'm going to talk about here is that, can we develop a simple analytical solution, at least in the case of a single fracture in matrix, which is a tractable problem. And while doing that, we also understood that there is a way to generalize this problem further. In the case of the weathering problem, the weathering mineral is an immobile solid phase. More generally, you could have a mobile, contaminant phase in the rock matrix. That would be of relevant from an environmental engineering perspective in the case of a remediation problem. For example, in the case of in situ chemical oxidation, you could have a TCE that is dissolved and remains stagnant in the rock matrix, and you're trying to eliminate it by introducing an oxidizing agent like permanganate or Fenton's reagent supplied through the fractures to try and react away some substance that is trapped in the rock matrix. So I'm going to present a general analytical solution for this problem of transport in a single fracture and matrix system where some reacting agent is supplied through the fracture and reacts with some other substance that is in the rock matrix. That some other substance could be either an immobile mineral phase, as would be relevant in the case of a weathering problem or a geothermal energy problem where you're interested in reactive alteration of the rock matrix over time, or in the case of an environmental engineering problem, that substance that is trapped in the rock matrix could be a contaminant that you're trying to get rid of, like TCE. And before I look at the fully detailed fracture matrix problem, let's just look at the simple 1D diffusion version of this problem. We saw the 1D advection version earlier. We can look at what happens in the 1D diffusion version now. And again, for generality, I take the harder problem, where the B that is trapped in the rock matrix is a diffusing phase, meaning it's not stagnant. The math is slightly easier if the phase that is being reacted with in the rock matrix is stagnant, like a mineral phase, a solid phase. But if it can also dissolve, if it can also diffuse, the problem is slightly harder. So I'll do the more general case, and the simpler case just comes about as a special case of the more general case. Okay? So let's consider a case where we have some substance B at some initial uniform concentration in the rock matrix. If that is TCE, for example, it's then reacting with some oxidant that is supplied in the fracture to produce some reaction products. If I look at just what's happening in the rock matrix alone, the fracture matrix interface is where I'm supplying the oxidizing agent, and then I have some thickness of rock matrix. I initially start with some B everywhere in the rock matrix. What we're asking is, what's going to happen if I bring some A here and allow it to react with this B? So a simple model problem where I have a no flux boundary at some distance into the rock matrix, and then I inject some oxidizing agent in the fracture at some concentration A naught. We're asking what happens once I inject this A naught here, which allows it to react with this B. What will happen in the rock matrix if I maintain this concentration at A naught in the fracture here? You would solve this problem with a couple set of reaction diffusion equations, one for the oxidant and one for the other substance that is in the rock matrix. If that was a diffusing substance, you have to write a reaction diffusion equation for that also. In the case of a solid mineral, that diffusivity of B would be 0, so it would just be a mass balance equation with the storage term and the reaction term for the solid mineral. Okay, so solving these two equations numerically, for example, with the Newton-Raphson type implicit method, what you can see is that let me just show the simulations first. What you'll see with time is that the profiles of the oxidant are going to look like this, that I maintain it at A0 in the fracture. It's reacting with the B that is in the rock matrix. With time, I deplete the B. When I do that, the A can diffuse farther in. And as I deplete, I will, as it moves farther in, it's going to deplete more of the B, sort of pushing the B out as a sort of a reaction front. But unlike the advective reaction front case, in this case, it's a diffusive reaction front. What we find typically is that there is a region of overlap between the A and the B concentrations where you get this peak in the reaction rate. And this zone within which significant reaction occurs is a fairly thin zone. And furthermore, it's a moving zone. Okay. So the question is, how do we capture the behavior of this system analytically? And the way that's done, going back in the literature to about the mid-80s or so, is that you can capture this behavior by invoking the idea of a moving boundary solution, inspired by the Stefan type problem, which is common in heat transfer with phase change, for example. So you approximate the system as one where you have two subregions. In one region, there is no B. In the other region, there is no A. In the left region, there is just diffusion of A. In the right region, there is only diffusion of B. They meet in a thin reaction zone in the middle, in a reaction front where the reaction is actually occurring. And to actually describe the system fully, you need to figure out the dynamics of this reaction front. In other words, you drop the reaction terms in the left half and the right half. You just treat them as non-reactive diffusion equations. And they have to come together in a reaction zone or a reaction front. But to actually solve the problem, you trade off this nonlinearity in the reactions with a different nonlinearity, which is that you have to describe the motion of the reaction front as a moving boundary. Okay. And essentially, you can neglect the thickness of the reaction zone. You can assume that it has 0 thickness, but you have to come up with a way of describing the behavior of Z equals Z of T, the reaction front, in order to complete the solution of the problem. This is classical example of what's called a Stefan problem, or a moving boundary problem, which traces back in the mathematical physics literature to actually a heat transfer problem with phase change. It's a boundary value problem in which the boundary between the phases moves with time. And in the classical Stefan problem, they need what's called the Stefan condition, which defines the dynamics of the moving interface. In the context of heat transfer with phase change, that Stefan condition is basically an energy balance condition, that in order for the phase change interface to move at a certain velocity, you should be supplying heat at a certain rate to the interface from one side. And you can use that condition then to formulate the dynamics of the moving boundary. The same way in the reaction diffusion problem, you have two conditions at the reaction front or the moving boundary. The first is that both A and B go to 0 at the location of the reaction front. And the second is the so-called Stefan condition, which rather than an energy balance condition, in this case, it becomes a mass balance condition. And the mass conservation condition really is just simply saying that, hey, I know that A and B are both getting fully consumed inside this reaction zone at the reaction front. So that means the supply of A and B into the reaction zone should be in the stoichiometric ratio of the reaction. So for example, if M moles of A are reacting with N moles of B in the reaction, then the diffusive fluxes into this reaction zone or to the reaction front should be in the ratio of M by N. Okay. So that is the equivalent of the Stefan condition in the heat transfer problem for the diffusion reaction problem. And insofar as these concentration gradients, del A, del Z, and del B, del Z, can be obtained by looking at solving these non-reactive purely diffusion equations, then we can close the problem to develop this condition in a mathematical form. Once you do that, the solution of the problem is complete. You basically, you can get an equation, at least an implicit equation for the propagation of the reaction front ZF of T. What we find is that ZF of T would have a diffusive scaling, meaning that it propagates as root T. The diffusivity that controls that motion is, we can call that a reaction front diffusivity. It's related to the diffusivities of A and B, and it's obtained from this implicit equation. In general, you have to solve this implicit equation to find DF in terms of DA and DB, the effective diffusivities of the two species. And in in some simpler cases, you can simplify this further. You can take advantage of that solid density asymptotics to come up with an even simpler form, which we'll see in just a little bit. One of the important thing about these systems is that the reaction kinetics does not matter in the end. The overall behavior of the system is diffusion controlled, and the reaction rates don't matter. All that matters is that the kinetics are fast. In most cases in porous media, the diffusivities are so small that the reaction is fast compared to diffusion, so that regardless of which species are involved, all that matters is the diffusion properties and not the actual reaction rates and reaction kinetics and so on. And here's again a comparison between the analytical solution and the numerical simulation for the reaction front propagation. We can, in this case, confirm that the propagation is going as square root of time, and also confirm the theoretical value of the constants involved in the root T propagation. So now the question is, okay, what really happens in the case of a fracture matrix system? That's a slightly more challenging problem. What we have in this case is a fracture into which an oxidant or some reacting species is injected, which is reacting with some other substance B that is in the rock matrix. The fracture and the matrix initially contain the B and maybe other substances that can react with the oxidant. We then supply the oxidant through the fracture and want to know what's going to happen next. We've seen the behavior previously in a purely advective system, in a purely diffusive system. In the case of a fracture, this is an advective diffusive system of an unusual sort. It's not the traditional advection diffusion problem in which advection and diffusion are occurring in the same flow domain. What we have instead is advection in the fracture connected to diffusion in the fracture. Okay? Connected to diffusion in the rock matrix. And the two are coupled by the interface boundary condition. So the question is, how does the behavior work out in a system like this when we have advection in the fracture coupled with matrix diffusion, and then we have a biomolecular reaction thrown into the mix? And it turns out that the behavior can be thought of in this way. To actually model the problem, you can write down the transport equations. Basically, what is required in the mathematical model is that you have to write down the transport equations in the fracture for the species in the fracture, the species concentrations in the fracture, both A and the B. Those are just simply the advection reaction type equations. You can add a diffusion dispersion term in the fracture if you like, but it turns out not to be so important. More importantly, you have the fracture matrix exchange term that is the key determinant of the behavior of these systems. And then you also have the bimolecular reaction in the fracture and in the rock matrix. In the matrix, you write similar transport equations for A and B. Those are just the diffusion reaction equations. And if you have both a mobile and an immobile species in the rock matrix, you have the diffusion for the mobile species. You just have the reactions term for the immobile species. You can have multiple species interacting with A. All of these problems can be worked out with a common framework that again assumes the occurrence of a sharp reaction front that separates the system into two parts, one in which A exists and in the other in which A is depleted. Okay? Meaning the weathering agent is fully consumed somewhere inside the system, and where it's fully consumed, you have a boundary that forms, if sort of a virtual mathematical boundary, a moving boundary whose dynamics we then have to track to describe the behavior of the system. So we can think of it this way. You have a constant rate injection at some flux Q with a constant concentration of the reacting agent, A equals A naught. The initial conditions fully in the system that you're injecting this into. You have some other substances, B and N, that are in the fracture and the rock matrix that are going to react with the A. And initially, there is no A in the fracture or in the rock matrix. What happens with time in the system looks like this. Again, invoking the fact that the reactions are relatively fast compared to diffusion in the porous matrix, which is always slow, controlled by molecular diffusion, you basically form a moving boundary like this, that there is a region near the entrance where you have non-zero A, and there is a region out, farther inside, which is demarcated from the region in which you have non-zero A by a reaction front in the rock matrix and in the fracture that has this tapered shape that looks like this. Beyond this region, A is 0. And we can define this reaction front in terms of two variables. One is xf of t, the tip of the reaction front in the fracture, and zf of x and t, which is the shape of the reaction front in the rock matrix. Both of these need to be determined as part of the mathematical solution. And as in the previous 1D problem, you basically assume that because I don't have any B or N in this depleted region, I can write a non-reactive transport equation set here. Similarly, in this region, I have A equals 0. I can write non-reactive transport equations here. And then I find a way to meet them at these interfaces to then complete the problem and describe the dynamics of this moving boundary zone in order to complete the solution. Okay, so it's kind of an extension of the classical Stefan problem to an advective diffusive type of Stefan problem. And to solve this problem, the approach that I came up with was to invoke a composite similarity variable. If you recall how diffusion equations are solved, we can invoke a similarity variable to obtain a solution. You convert a PDE into an ODE, and then you can solve the ODE to get your Gaussian or error function solutions. Same way, in this case, we need to invoke a composite similarity variable, meaning that because the problem is occurring in 2 dimensions, x and z, we create a composite similarity variable that's a combination of x and z. And there are these constants alpha and beta, and alpha prime and beta prime that we put into the composite similarity variable. All of them can be determined in the end self-consistently by assuming a form for the solution, putting it back in the PDEs, much like in the similarity approaches to solving diffusion like PDEs, and then obtain the functional forms for these functions f and g that are here. F are the shape functions for the solutions in A, G are the shape functions in the solution for B. Mathematical machinery here is exactly the same as a similarity approach to solving diffusion equations. You substitute these forms into the original PDEs, they'll then generate ODEs, you solve the ODEs then to obtain these functional forms. I'm not going to dwell a whole lot on that. I had a slide on it, but let me just skip it. I said that in words already. All of this is based on the similarity approaches for solving diffusion-like equations. All we're doing is, in the classical diffusion equation where we use a similarity variable with just one space variable, we are making a composite space variable here that has both x and z in it. And the other adjustment we have to make, of course, is because B is only starting on the other side of the reaction front, we have to use lag variable x minus xf, for example. Okay. You can determine the functional forms of f and g. I'm not going to go into the details. Obviously, they do involve error function type functions in them because they're coming from a solution to a diffusion-like equation. I'm not going to go into details of the mathematical form. What's important is that we are able to obtain unique mathematical solution. And once we do that, the behavior of the reaction front is fully categorized. And it turns out that for a whole class of reaction front propagation problems in fracture matrix systems, the behavior is more or less the same. It turns out that the ZF of x and t is approximately linear. It decreases from some entrance value, which is obtained by the solution for the purely 1D reaction diffusion equation, the Stefan problem that we saw earlier. A linear decrease from that, which then brings it to the location xft, where ZF of xt goes to 0. Okay? And although these equations look a little more complicated, essentially to a very good approximation, this is what they involve, that ZF of x and t decreases linearly with x until it goes to 0. It goes to 0 at the location xf of t, which is some Peclet number-like quantity multiplied with ZF 0t, which is the reaction front width at the entrance, which is occurring just by diffusion and reaction at the entrance. Okay? So, and this behavior has previously been noticed in numerical simulations in single fracture matrix systems, and we were able to show how this behavior results analytically. And these analytical solutions now are a very powerful tool for benchmarking numerical simulations, especially in the case of problems involving fractured rock, where matrix diffusion is very, very small quantity, but then controls over long times. You need to have very fine discretization near the fracture matrix interface to capture matrix diffusion accurately. You can verify those kinds of numerical codes based on these analytical solutions. To determine this quantity df naught, again, what we saw earlier was that you get an implicit equation through the Stefan condition. And again, that all I'm showing that here in this case of a problem where we have both a diffusing species and a mobile species, that Stefan condition is a little more involved. But in the end, it leads to an implicit equation that you can solve for the reaction front diffusivity. Once you have that, then everything in these equations is fully obtained, and you can get the linear decrease of CF with X, and also the location of XF of T, which is an important variable in the propagation of the reaction front jointly in the fracture matrix system. Well, you can use this analytical solution for benchmarking, but also to believe me, you have to see that I can show a comparison with very high resolution numerical simulations and show that the analytical solution captures the behavior in those numerical simulations. And you can see that here I'm showing a comparison between analytical and numerical solutions. You can see that the agreement is quite good, except very near the front where, clearly the sharp front approximation is only an approximation. It's remarkable that it actually captures his behavior so accurately, but very near the tip of the reaction front, obviously, where we have diffusion in the real world, and we are approximating that as a sharp front in the analytical solution, it's going to miss something, but overall, it's quite accurate. Some other comparisons here in the rock matrix at different locations. Again, you can see that the comparison between the analytical and numerical simulations are analytical solution and numerical simulations are quite accurate. Again, validating the analytical solution, if you will. In a way, it's a verification that the analytical solution actually is correct. There are no mathematical errors in it, and it provides a meaningful description of these fairly complex behavior in a fracture matrix system. This shows the behavior of the reaction front in the fracture matrix system, showing both XFT and ZF of XT. It confirms the linear variation. There's a slight offset between the numerical and the analytical here. That could also be because of discretization errors in the numerical solution, and may also be because of approximations involved in the sharp front type solution to this problem. But regardless, the behavior is captured quite accurately. And so this is a powerful set of analytical solutions for investigating depletion of minerals or contaminants in the rock matrix by the supply of a weathering agent or a reacting agent in infiltrating water through the fractures. Okay, so this is addressing a large range of problems in geothermal energy, in critical zone weathering, and also in contaminant remediation type problems. Again, I'm going to show a little animation of this, looking at an A-B reaction type problem. So A is what is being supplied from the fracture, and B is being depleted from the rock matrix. Again, comparing the numerical in the left frame with the analytical in the right frame. You can see the propagation and depletion. You can see A getting consumed inside the domain and B getting depleted simultaneously. And the comparison between the numerical and the analytical is quite encouraging, even in a 2D sense. It just more or less confirms what we saw in the earlier line graphs. Basically, you can see the advance of A, showing that reaction front being linear, and then a tip forming in the fracture, and then B being zero on inside the zone which is getting filled by A, and then almost undepleted outside of that reaction front region. So going from these simulations to explain some of the things we saw earlier, which is like the time dependence of the system integrated reaction rate that we saw in the simulation in the more complicated fractured rock system. Excuse me. Basically, what we've seen from the analytical solution so far is that we can show that XF of t has this Peclet number times root t propagation. It propagates as root t. Even though we have advection in the fracture, the overall propagation of the reaction front exhibits a diffusive dynamics, which is scaled by Peclet number times root df naught t. Df naught, in fact, is very approximately just given by the ratio of A naught by B naught, multiplied with some other constants. The system integrated reaction rate, as you expect, would be constant as long as this reaction front is fully contained inside the domain. Because what that means is that all the A naught that you're supplying in the inflow is getting consumed if I have a situation like this where the reaction front is fully contained in the system. It means that whatever A naught I supplied is getting reacted inside the system. That means just by mass balance, the reaction rate has to be a constant. As this progresses, we'll get to a situation where the reaction front reaches the end of the system, or the outflow end of the fracture. At that time, we can actually calculate the time analytically. It's the inverse of the Peclet number square times L square, the length, divided by df naught. Okay. And when the reaction front reaches this outflow boundary, then at that point, this chemostatic condition is no longer valid. The reaction rate is no longer constant because some of the A that is being injected can still leave the system without being reacted. At that time, at later times, the reaction front starts to look like this. And in fact, we can show theoretically that for times greater than this time TL, when the reaction front reaches the tip, the outflow tip of the fracture, this reaction rate starts to decrease as 1 by root t after that. It starts from this constant rate and then starts to describe this 1 by root t decrease. And the time dependent that we saw in those earlier simulations essentially is a 1 by root t decrease that is coming from a diffusive type scaling. We can capture that more or less faithfully based on this analytical solution that we can see in a single fracture rock matrix system. One other possibility to consider is where the matrix width is limiting, in the sense that where we have a situation where the reaction front propagates as root t both in the z direction and in the x direction, then we don't have any boundary effects. In the previous slide, we saw what happens when we have the boundary effect where the reaction front reaches the outflow boundary first. The other possibility is that the reaction front reaches the matrix width first. It's still contained inside the system along the fracture, but then it reaches the boundary of the rock matrix, which would happen, for example, if you had a finite rock matrix thickness, finite size rock blocks, for example. So in that case, these analytical solutions that we derived earlier only persist as long as ZF0T is less than W, meaning the reaction front reaches the edge of the matrix at the entrance to the flow system. Until then, dxf dt scales as 1 by root t. In fact, it's decreasing progressively with time. And what happens after that is the behavior that looks like this, that you have a depletion over the entire rock matrix width. And then this fluted shape here is found at the edge, at the bottom end of that propagating reaction front. In fact, this dxf dt decreasing as 1 by root t, that only occurs until this time tw, when the reaction front extends over the full matrix width. And after that, it becomes constant. It reaches a new small value that is something we can reason just from mass balance. You can just calculate a mass balance argument for, okay, if I want to make this thing, this depleted region propagate, I need to move this location here by a certain amount dz in a certain amount, in a certain time delta t. We can calculate that rate just like we did in the very first advective exercise. And we find a retarded rate of propagation of the composite weathering front in the fracture and the rock matrix that we can also calculate analytically. And we're currently involved in trying to understand the behavior in more complex fractured rock domains by starting from the parent analytical solution and including these two additional possibilities. The possibility of the reaction front reaching the tip in any dominant fracture flow path, and also the case where the reaction front can extend over the full matrix thickness and then start to create a behavior like this in some of the matrix blocks that are getting fully depleted. So in a more complex fractured rock mass, both the matrix block width and the travel time through a dominant fracture flow path would vary. And so the question then is, okay, what happens in a system where we have those kinds of variations? Part of that extension, comes about by using an advective travel time transformation. Basically, if we look at the behavior in these systems as advection along streamlines that are in the fracture, communicating with the rock matrix by diffusion, we can make use of a convenient coordinate transformation called the advective travel time coordinate transformation, where in the normal fracture transport equations where you have the advection term in the fracture that has a non-constant velocity in the case of non-uniform flow or heterogeneous flow, if we define streamlines and then define an advective travel time coordinate along the streamlines, it turns out that you can transform this non-constant coefficient advection operator into one where there is a constant coefficient advection operator. And once we do that, all these analytical solutions can be extended for these non-uniform velocity fields as well. That can be either forced gradient type flow fields that you get in a remediation type context, or more complex streamlines that you get in random fracture networks. And we are making both of these extensions. For example, in these simple cases where we have non-uniform flows in forced gradients, which are also having some analytical results around them, what you can show, for example, is for radially divergent flow, which is this flow here, injection well, through which we are supplying some remediation agent. You can theoretically show that you don't have a linear decrease of ZF of XT like we had in the previous case, but a quadratic decrease ZF of RT. And in fact, in this case, the remediation front propagates as T to the 1/4 rather than T to the half that we saw in the 1D linear system. In a 2D radial system, it turns out to be T to the 1/4. Again, this is something you can reason from mass balance. You can also reason this from a travel time coordinate transformation and develop an analytical solution essentially in any in travel time space for any complex flow field. In particular, these simpler non-uniform flow fields, you get the systematic results like the T to the 1/4 behavior. And for the injection well in a uniform natural gradient flow, for which there is an analytical solution for the equal advective travel time contours, you can again calculate the behavior of the remediation front in a system like this. It would be much more slowly propagating compared to the non-reactive advective travel time front. Okay? And we are currently involved in taking these analytical solution concepts and trying to use them to interpret the behavior in more complex fractured rock masses that have networks of fractures with all sorts of complexities, capturing the complexity of advection in streamlines and travel time distributions, and combining that with our analytical concepts for fracture matrix interaction and bimolecular reaction. So with that, I'll conclude. Basically, I showed a similarity-based solution for bimolecular reaction transport problems in fractured rock. The novel element in this approach was the introduction of a composite similarity variable that actually produces then a means for solving these problems analytically. The similarity solution agrees well with numerical solutions. The highlights are that the reaction front tip in the fracture propagates diffusively as root T. The reaction front geometry in the rock matrix shows a linear decrease with X, starts from some square root of T width at the entrance to the flow system, decreases linearly until it goes to 0 at the composite reaction front that is found at the tip in the fracture. This behavior is true for a large class of reaction front propagation problems in fractured rock that include problems where we're interested in contaminant remediation, reactive alteration in geothermal systems, or natural weathering problems in the critical zone. I showed the extensions of these solutions to describe behavior when we have boundary effects, where the reaction front reaches either the end of the flow system, meaning the outflow end of a fracture, or extends across the full matrix width, and essentially the matrix blocks get fully depleted. Again, sort of philosophically, to sum this all up, numerical simulation of this type of reactive transport with matrix diffusion in 3D fractured rock is only just now beginning. It's a challenging problem computationally because you get sharp concentration gradients near the fracture matrix interface because matrix diffusion is typically a small quantity. You have to run these simulations over very long times. It's often tempting to make the matrix discretization a bit coarse, but if you do that, you might lose accuracy. And our analytical solutions would be helpful, for example, in building hybrid numerical analytical models, and also for benchmarking coupled process simulators that are increasingly trying to simulate these processes at least over engineering timescales of the order of decades for geothermal energy systems or CO2 sequestration systems. So thank you for attention. I'll stop there. Sorry, my voice was giving out a little bit. I'll stop there and take any questions. Thank you again.
Thank you very much, Professor Rajaram. Yeah.
Okay, so we'll open the floor for any questions. Do we have any questions? So we have a few in the, we have already a few in the Q&A. So
maybe I'll start with them and maybe try to walk through them one by one. Okay. So the first one is from Bhaivaswata Baduri, and the question is about hydrodynamic dispersion. Is it possible to simulate that as an intermixing between a bunch of mobile and immobile compartments? Let me put it this way. I don't think that fracture and matrix interaction can be properly captured with an advection dispersion-like equation over the timescales of relevance in these types of problems. In the sense that if we look back even at non-reactive transport and we compare the behavior of transport solutions for advection dispersion in the fracture combined with matrix diffusion, it produces a tailing behavior that is completely different from what we would get in a conventional advection dispersion-like equation. Now, it may be possible with some non-Fickian ideas like continuous time random walk or something to mimic the behavior in the fracture matrix system with unconventional non-Fickian type advection dispersion equation. But otherwise, in a lot of these cases, the use of multi-continuum type models with compartments, mobile and immobile, will really not capture this type of physics very well, especially because one thing you can see is that these moving boundaries, the way that they are creating a diffusion types, a persistent diffusive scaling, that's something that's typically a challenge to pick up in these multi-compartment type models. Let me go on to Jishma Jayan's question. The impact of using additives to seal fractures for tunneling. This is, unless there are reactions between the additives and the rock matrix problems, the work that the rock matrix materials, the work that I presented here is not relevant for the problem of sealing rock fractures with a sealant. Those would probably be more in the realm of non-Newtonian flows in fractured rock, which would be like injection of grouts and other sealants. There's really not much transport involved there. Probably a multi-phase flow type problem, or even a single phase flow type problem that involves a non-Newtonian rheology. Did you consider the fractures of the roughness of the fracture? If so, how? In most of my early career, I worked on problems where I worked a lot on the influence of fracture roughness on flow and transport at the single fracture scale. At some level, that that behavior can be captured by using the streamline coordinate transformations. Mainly what it results in is heterogeneous advection, right? You can capture that fairly readily by using the streamline coordinate transformation I described at the end. But that being said, oftentimes when we have fracture matrix interaction, the overall transport behavior that is resulting tends to mute out the influence of that heterogeneity and preferential flow at the single fracture scale. This is mainly because matrix diffusion is a retarding mechanism. It tends to sort of equalize transport across multiple flow paths. Although you can extend these ideas to situations where you have fracture roughness, when we look at large complex fractured rock masses, likely the complexity at the network scale dominates over what we see as roughness at the single fracture scale. That being said, I myself worked for a large part of my career on single fracture scale problems looking at roughness. It's convenient to do experiments at that scale, and you see a lot of complexities at that scale also. Just that when we want to model field scale systems, I think the larger scale heterogeneities in the end dominate the overall behavior. That's at least my bias. This is a repeat question. Then there's a question from Bukhya Pavan. Flux conditions of B or 0 at the end of the geometry. I'm sorry. Basically, these are, the flux condition, the flux boundary condition for B is just a symmetry boundary condition, if you will. If we're looking at, if you're looking at a situation where we have equally spaced fractures, then it's like the half spacing between the fractures. And even otherwise, you're bound to have a boundary at the edge of a rock matrix block, for example, before you meet the next fracture. In the real system, we may not have, in a real numerical simulation, we may not have to specify these boundary conditions to simulate a system fully, because the reaction fronts from adjacent fractures penetrating into the same matrix block, they're going to come together somewhere and become a combined front, right? That part can easily be captured in the numerical simulation. It's only for the purpose of analytical solution that we need to introduce these flux condition, these Neumann boundary conditions to define the finite width of the rock matrix. Is this relevant to bacterial flushing to groundwater remediation? The reason why I think it is not that much relevant is because often when you're trying to do remediation of deep fractured rock systems, they're not in very oxic environments. So bioremediation is often not an alternative. That's why they use in situ chemical oxidation instead, because once you get to the depths where you have fractured bedrock, typically the waters are not oxic. It's very hard to stimulate bacterial growth. And even if you do, one of the problems with doing that in a fractured rock system is that if you create bacterial growth that clogs the fractures, then you're defeating the purpose of your remediation, because you really cannot produce remediation over very large distances, because you'll be clogging up your fractures and not allowing the substrate and other agents that you're injecting to travel very far in the fractured rock system. I think I've caught up with the last, oh, there's one more. Sudipta Roy. Yeah. Oh, many more. Okay, great. 1 minute. I'll just keep going down through the system. One more. Let's see. Let me see if I can get to it again. Where are the, I'm losing them. Hang on.
I also don't see that Sudipta Roy's questions. I don't know.
Yeah, it was there a minute ago, and then it's.
Yeah. I saw that.
Okay, you can just ask me perhaps verbally, and I can answer it.
uh, I, for that, I think she need a permission probably.
Or if somebody
Yeah.
wants to type in again.
Yeah, she may just post it again if relevant. Otherwise, we can move on with other questions if there are any from the audience.
There's another question. I think it is by RSR.
Yeah, okay,
Yeah,
got it. That I answered just
yeah,
now.
he just answered. Yeah.
Okay, right. Then I think done. Okay. Something I think the chat box also. No, I mean.
No, I think that's just a comment. I think that's all
Okay.
there is.
Oh yeah, I think Sudipta Roy's question is coming up again now. When salt is produced from natural sources, how can we make assumptions of solubility for? I'm sorry, I don't know. I'm sorry, I'm not sure if I can answer that question.
Yeah, okay. Thanks once again, Professor Rajaram, for a very interesting talk. So I just had a comment to make. Your point on the last slide about having analytical solutions ready for 3D fractures is very, I can relate to it quite a bit because these things, as you said, with sharp gradients can get really expensive, especially when there is some scale disparity. Or some sharp gradients, and sometimes the simulations can take a really long time. So having some analytical solutions or a semi-analytical approach where we could feed those into the numerical solutions could really make jobs of numerical scientists a lot easier. That's a very, I could relate to it quite a bit.
Yeah, and our hope is that maybe the only pragmatic way of solving some of these problems at the practical level is that if you can generate streamlines from the flow simulations, which are actually not so computationally demanding, but then for transport, you then use these semi-analytical solution-based approaches along streamlines. That's a practice that's already done, just that the analytical solutions that I showed are for this class of alteration problems, which I think have not been addressed in the literature a whole lot previously. And as I'm saying that, I also realized there are some questions in the chat box in addition to the Q&A box, so I could also address them if there is time.
Yeah, absolutely.
Okay, so there's one that says depletion minerals are slow but not fast. Yeah, that is, again, what I said earlier, that if we look at the molar density of a mineral inside the solid, it's typically very large, right? So for example, if you say how many moles of calcium carbonate are in 1 cubic meter of calcium carbonate, that's a large number of moles, right? We know, we can make that calculation. And then we ask the same question, okay, suppose I take 1 cubic meter of water, how much calcium carbonate can I dissolve in it? How many moles? That is constrained by the solubility. So when you took a look at that ratio, you'll find that it's in the order of 3 to 4 orders of magnitude. And that is why typically you have to flush a lot of water through to deplete any mineral composition significantly. And that's why the mineral depletion is typically slow. Yeah, to answer Dr. Longino's question, yeah, I think that this field of critical zone science, which there's a new term now, AGU has a keyword called critical zone science. It's really bringing together hydrologists, geochemists, and geologists to work together on some long-standing problems. And one of our hopes is that it will provide a way of making more improved quantitative models of complex geological processes. That is sort of a grand challenge in a way. I mean, historically, simply because of the complexity of the system, we had qualitative descriptions of what happens. And I think we are at a point now where we can all combine forces and address these problems more quantitatively. I think that's it. I don't see any other questions.
Yeah, I think, yeah, Abhijit, please.
No, nothing. I think there is no more question. I don't see anywhere in both Q&A and chat box. Yeah. No, I mean, I think I need to go through your presentation. There's a lot of things I need to learn, understand it a bit more details. Then I'll ask you separately. That privilege I have anyway. So
Sure.
I think,
Yeah, of course. And any of you, if anybody
Yeah,
has any further questions, happy to
Yeah.
respond by email also.
Yeah. I remember you talked one thing about the heat transfer process, and this is much more complex. I mean, I mean, in the Podas Media course, I think you taught a similar thing, the analytical solution with the Eros function. I think this is much more complicated than, but that bit of similarity. Then
Yeah, there are two sides to it. One is that honestly, I struggled a little bit to find this analytical solution.
yeah, it's
And but surprisingly, it's simpler than the
Yeah.
non-reactive case solution, because in the non-reactive case solution, you have to generate the solution by inverse Laplace transforms, right? And they're
yeah,
not
I remember.
always.
Yeah, I remember that. Yeah, yes.
But in this case, actually, it turns out that the existence of these sharp fronts, actually, with the similarity transform approach, actually makes a solution quite easy. And in fact, you can use this similarity variable approach to solve the non-reactive problems for heat and mass transfer in fracture matrix systems. And you actually get the same answer as the Laplace transform solution. That's another way of verifying that the math is correct.
Yeah. Okay. Yeah, it's wonderful. I think I need to read it. I'll go through it, your presentation. It is recorded, and I'll see.
Sure,
Then
thank you.
I'll
And I'm also, I'm also sort of sorry that I gave a more detailed presentation than a more high-level, big picture type presentation. But one of my, I'm an old man. I like to see the younger generation not forget. Nowadays there's a lot of temptation. We have a lot of high-performance computing tools. A lot of things like machine learning are coming on the horizon. But at the end of the day, it's always nice to have clear physical conceptualization at a level where we can always come back and reason something through analytical solutions. And provided you did the math correctly, there cannot be anything wrong about an analytical solution, right?
Yeah.
And so in that sense, it serves as a benchmark for a lot of more complicated problems. And I like to see that tradition continue in the next generation also.
Absolutely fine. I think the details is absolutely needed. I mean, for this is the purpose of this way. I mean, webinar anyway. Yeah, so it's all right what you did. Yeah. Okay.
Yeah.
Ramesh. Yeah.
Yeah, I think it's good. Chandra,
Yeah, no, I don't have any other question. Thanks very much, I think, for a very insightful talk once again. Like you said, in finite element method, we are often using some functions called as enrichment functions to make sure that we capture these mesh gradients well without actually refining them. So your solutions could probably be very helpful in from that perspective as well for us. So yeah, thanks again. I think because there are no further questions, yeah, so we can end the